So here we are. You should see my note screen. Okay. All right, so 13.4 is called the fundamental theorem of calculus. So it sounds super important, and it is really super important. In the scope of this class, you'll find that while we use it in this one section, we don't really use it a lot else. But it is something that ties in the concept of derivatives and antiderivatives together. So it is this fundamental theorem. I'm going to show you. So the first thing I want you to do is remember our antiderivative notation, what it means. We're going to talk through just what we've been doing. So I take the antiderivative of some function, let's call it f of x dx. And remember, I always try to think about this as a change function, like this is the derivative of something. And when you take the antiderivative of this, what you get, and I'm going to call this capital F, is the original function that came from. And we have the plus c because I know when I talked about taking an antiderivative just in general, we found that there could have been a constant there that wouldn't be present in the derivative function. So I always have to put that plus c to allow for any constant to be there. But you guys, the fundamental theorem of calculus looks a lot like this, and it starts out the same. So I'm still having this antiderivative of some function f of x dx. But you guys, I get bounds on my integration. So I want to take the antiderivative of this from a to b. So the way I want to integrate, you can say antiderivative. A lot of times we just use the word integrate here, but I want to integrate f of x from a to b, and I want to know what my answer would be. So if I actually had limits on this function, what I end up getting is I still get the original function, but those bounds get put in here too. So what it ends up being is that I get the original function evaluated at my top bound at b, and then I subtract the original function evaluated at a. So the best way I can think to put this in understandable terms is that this is change, right? This is the change of the function f. And I want to integrate the change from a to b, which means I want to find the total change from a to b of this function. And to find that total change, what I do is I find the original function at these two endpoints and I subtract. So that should make sense. The total change from a to b would be the value of the function at b minus the value of the function at a. You do have to integrate first and then put in your a and b. So you might wonder where the c is in this theorem. So this is the theorem, and there's no plus c. You might wonder where it went, but you guys, what's happening here is you're having your original function at b, and then you're subtracting it from you're subtracting the function at a. Each of these would have their own plus c. So if you think about it, this would look like, you know, you take the antiderivative and you get f of x plus c, and then you evaluate that at b. Then you take it and you get f of x plus c again. Remember, you get the exact same integration, but this time you evaluate it at a. And when you do this subtraction, notice that this plus c and this one would actually be a minus c. The c's actually cancel each other out because you're taking the antiderivative at two different places and subtracting. So the c's do cancel out. You don't have to write plus c when your integration is bounded. So that's good news. It's something you don't have to remember. Remember, in 13.1 and 2, definitely you need that plus c. But in this 13.4, you will not have a plus c at all. So you guys, using this fundamental theorem is actually pretty easy. We just integrate as normal, and we put in the bounds after we integrate. So let me show you on this easy example here. So notice I've got here, I want to integrate from 1 to 3 the function 2x dx. So it starts out normal as if there were no bounds. You guys, I do integration. How do I do that? Well, this is 2x to the first, yes? What do I do with a coefficient when I integrate? Well, I just bring it down. So I bring down my 2. You guys, if x is to the first, remember with the power rule, we think about that n being 1, and then n plus 1 would be 2 in this case. Remember what the power rule for antiderivatives is. It's 1 over n plus 1, x to the n plus 1. Remember, I don't need a plus c because I'm going to take this function and I'm going to evaluate it at 3 and at 1, and I'm going to subtract. And notice how I put it in a bracket and then I put the bounds on the outside. This is my notation for taking this function from 1 to 3. If you're doing your homework, you might see this, well, a little bit differently without the brackets. So let me simplify this first of all. So I have the 2 times the 1/2. That's just 1, right? This is really just x squared. In your book, the way they notate that going from 1 to 3 is they just put a straight line like this and put the bounds here. So you might see it that way. I've always done it with these brackets. Either way is fine. Don't let it confuse you and think that this is 2 different things. It's the same. But if you're doing your homework and you look for an example or something, it's going to look like that. Or if you're looking in our text, it looks like that with the straight line. But anyway, it means the same thing. So what it means is I need to take that x squared, evaluate it at 3 first. So you guys, what does it mean evaluated at 3? It means put a 3 in here for the x. So I get 3 squared, and then over here I evaluated at 1, so that's going to be 1 squared, and I subtract between the 2. Making sure that your larger bound, so your top bound always goes first and your lower bound goes second. Because if you switch them around, you'll get the same value, but it'll be the wrong sign. So maybe it'll be negative when it should have been positive, or vice versa. So I have here 3 squared minus 1 squared, so that's 9 minus 1. And I get an answer 8. So you want to simplify within each bracket, and then once they're down to one number, you can do the subtraction. And you guys, my answer here is just 8. It's just a real number. There's not going to be any variables in it because remember, you've replaced the variables with your bounds. So let's look at this next one. We're going to do the same exact idea, integration first, then put in the bounds and subtract. So x to the -5th, you guys, the power rule where n here is -5 and m plus 1 would be -4. Well, that's going to give me 1 over -4 x to the -4th as your integration. Remember, we don't need a plus c, but what we do need is to notate we're going to take this at the bounds 0 and 4. So remember, put in the 4 first. That looks like -1/4 times 4 to the -4. So I put the 4 in there. Now here I'm going to put the 0. Make sure you subtract in between. I get -1/4 times 0 to the -4. So let's see what I get. You guys, here, how do I take a number to a negative power? Remember, you can bring that down across the fraction bar and the power becomes positive. So 4 to the -4 is actually, I'm going to stick that 4 on the bottom. So there's already this 4 on the bottom. I can write this on the bottom as 4 to the +4. So a lot of times we're used to rewriting where if you've got like an x in the bottom, you bring it up with a negative exponent. You can bring it down and make it positive just the same, right? So here we have -1/4. You guys, 0 to any power is just 0. So -1/4 times 0 is what you get there. Okay, so let's figure out what this is here. I have the 1 on top. I have the negative out here. You guys, 4 to the 4th, you want to do that first. And in this case, it doesn't well, it does matter. 4 to the 4th, you want to do that first, and that's 256. Then multiply it times this 4. So ultimately, this is 4 to the 5th, if you want to think about that. But you should get 1024 on the bottom there. And then you guys, what happens to this term with this being a 0? Doesn't it just cancel out the whole thing? It does. So you end up with this minus 0, which is just negative 1 over 1024. It's nice when you're bound to 0 sometimes because it zeroes out one of your terms and then it makes it easier. We're going to see later, though, that just because you have a 0 bound doesn't necessarily mean that it's going to cancel out that term. So you always want to be careful and don't just assume. But in this case, that 0 did take care of that second term for us. So let's look at this one. So notice the difference on this one. I've been just doing a single term. We have multiple terms now, but it's still a basic integration, you guys. We just remember you just do each of them separately. So let's do the integration. First number, or the first term, is x cubed. So here the n is 3, so n plus 1 would equal 4. So your first term integrated is going to be 1 over 4 x to the 4th. Plus, we already integrated 2x earlier. It just turned into x squared. What happens when you integrate a constant? Remember, it just gets a variable. It just gets an x. So I just integrated each of these separately. Now I have successfully taken the antiderivative. Don't forget to now take it at these bounds from 2 to 4. So let's see what happens here. You guys, let's put the 4 in there. So I get 1/4 times 4 to the 4th plus 4 squared minus 8 times 4. So in this one, I put 4 in for everything. Now, in this bracket, I'm going to put a 2 in for everything. So I get 1/4 times 2 to the 4th plus 2 squared minus 8 times 2. And then I'm going to work each of these brackets separately. Then when I'm down to a single number in each, I will subtract. Okay, so I already know 4 to the 4th was 256. So that's 256 over 4. Make sure you, this one is not a negative exponent, so it does go on top. Plus 16 minus 32. Over here, I have minus, you guys, this 2 to the 4th, that is 16, and that goes on top. So it'll be 16 over 4 plus 4 minus 16. Simplify even further. So I know we have fractions here, but these actually divide out evenly. You guys, 256 over 4, that's 64. Plus 16 minus 32. Over here, 16 over 4, that's just 4, plus 4 minus 16. Let's do the add and subtract within each individual bracket. All right, you guys, 64 plus 16 minus 32 is going to be 48. Minus, over here, you guys, 4 plus 4 is 8. Minus 16 is actually negative 8. Be careful because now I have a minus, a negative. I'm going to make sure that that turns into a plus. So I have 48 plus 8, and I end up with 56. So here's my solution there. You guys will notice that in these problems that I'm doing, as well as your homework problems, the integration itself is the basic integration, like from 13.1. You're not going to have to do a u substitution integration on one of these definite integrals. So for this whole section, it's just the basic antiderivatives, just with that extra step of putting in your bounds. U substitution with a definite integral gets a little bit dicey. For example, when you turn an x term into a u, because you're integrating with u instead of x, your bounds have to change and you have to calculate what the new bounds are and all. It's just, it's not pretty and it's not something that we need to worry about. So this will just be basic integration. So let's look at this next one. You guys, I want to integrate from 0 to 5. The function is 6e to the 2x dx. So I know that the e to the 2x, we had some questions like that in the u sub, where we did use u substitution there, but we don't have to, because remember, if it's just like e to the 2x or e to the 3x or e to the negative 5x, if it's just a number here with the x, remember, we can use the basic integration rules with that. So that's what we're going to do. So we'll remember what those look like here. So the 6 is a coefficient, just comes down. What happens when there's a coefficient on x up here? So in this, we have e to the 2x. I'm making that look horrible. So I have e to the 2x. Remember, this 2 comes down in front, but not with multiplication. It comes down with division. So it ends up being 6 times 1 over 2. And then remember, the e term always comes down exactly the same. So I have 6 times 1/2 e to the 2x, and I'm going to take this and evaluate it at 0 and at 5 and subtract. You guys, on this one, really don't take this 0 for granted and think it's going to zero out that second term, because it will not in this case. All right, so 6 times 1/2 is 3. So this is really just 3e to the 2x evaluated from 0 to 5. Okay, so let's put a 5 in there first, and we get 3e to the 2 times 5 minus the function with a 0 in there, which is 3e to the 2 times 0. So let's see, what is 3e to the 2 times 5? Well, let's just call that 3e to the 10th right now and leave it like that. You guys, 2 times 0 is 0, so we get 3e to the 0. But don't automatically assume that that zeroes out, because what is e to the 0? Isn't that just 1? You guys, everything to the 0 power is 1. So what we really get is we have this 3e to the 10th minus 3 times 1. So really just minus 3. Now, MATLAB is pretty inconsistent on when it wants an exact answer versus a rounded answer. So you're just going to have to pay attention to your instructions, whatever it says. If it wanted an exact answer, this is where we would leave it. Because if you start trying to calculate with that e, it automatically is going to become a decimal approximation. So if it's exact, you leave it here. If it's wanting a rounded answer, just throw that in your calculator. You know you have an e button. So 3 times e to the 10th, and then minus 3. You guys, it's a pretty large number. I got 66,076 about 0.40 if I went to 2 decimals. It was 0.397, so I would get this, and it makes sense that it's a large number, because remember, e itself is between 2 and 3. It's about 2.7818 or so. So if you take that to the 10th power, it does get very big. So we get this large number as an approximation, exact, just the 3e to the 10th minus 3. So you guys, this one has the negative exponent. So it looks like one that we did before. I think we did x to the negative 5th. But you guys, this one has a little bit extra because we have the negative 1 power here. And we have to remember, when your power is negative 1, the power rule doesn't work. Remember, this is a natural log situation. So you guys, I'm going to rewrite it so you can more clearly see that this is a natural log situation. How could you rewrite 6n to the negative 1? Isn't that just 6 over n? And then I'm going to leave this as n to the negative 4 because that is just power rule. So remember, if you're looking at a fraction and it just has a variable to the first power down here, or in this case, when your power is negative 1, that turns into natural log no matter which way it's written. Any other power is going to be power rule. Literally any other power other than negative 1 is just power rule. So let's start integrating. 6 over n. So you guys, either way you look at this, whether the 6 is here next to the n term or the 6 is here on top, that's a coefficient. You guys, so you bring the 6 along, and I know that when there's just an n on the bottom or when it's n to the -1, you integrate by taking the natural log of the absolute value of the variable. Remember why the absolute values are there is because we're introducing this natural log statement. We know nothing about n. We don't know if it's positive or negative. But if you're going to take the natural log of it, it has to be positive. So we put the absolute values there to cover that. So that's what we get for integrating the first term. Let's integrate this second term. So you guys, if your power is -4, your n plus 1 is -3. So it's going to be 1 over -3x to the -3. Just normal power rule on that one. We're going to take that now that we've integrated and evaluate it at 1 and 5 and subtract. Okay, so there's not really any simplifying here to do, so I'm just going to get the 1 and 5 straight in there. So first let's put 5 in and get 6 times the natural log of the absolute value of 5. Now 5 is already positive, so in my next line I could drop the absolute values, but I'm going to leave them here. So you guys, this is plus, and then I have this -1/3. Let's just call that -1/3 times 5 to the -3. So I put the 5 in everywhere. Oh, sorry, I called that an x. It might not be confusing, but I don't want to confuse you. We're in n's here. It's habit. So here we go. Let's put a 1 in everywhere. So I have 6 times the natural log of the absolute value of 1. So again, 1 is already positive. So in the next line, you can drop the absolute values. Think about where they would be important, though. What if my lower bound was -1? Well, then I would put it in here and it would become a +1. But it is already positive, so I don't have to worry about that. Then here we're going to have -1/3 times 1 to the -3. Now let's try to simplify within each bracket. I'm going to leave the 6 natural log 5 as 6 natural log 5. If I wanted an exact answer, I would always leave it like that. And even if you want an approximation, you would wait till the very end to do that. So I have 6 natural log 5 minus, now this 5 to the -3 here, it's going to work the same way as that 4 to the -4 we had. We can stick it on the bottom and call it 5 cubed. So over here, we have 6 times the natural log of 1. Now, 1 to the -3 is the same as 1 taken to any power, right? This is just 1. So really, this is just -1/3. All right, so first bracket, keep simplifying here. We get 6 natural log 5 minus Hey guys, so if you're wondering where I just went, it's because our power just went out again. Hopefully this is not a permanent thing or a long-term thing, but it's out. So I threw on my mobile hotspot so we could finish this meeting. So let me make sure. It looks like everybody's basically back in here. So yeah, so sorry about that. Awesome. So anyway, so here we are. Hopefully the internet's not bad. I think the hotspot's usually pretty good. But here we were, you guys, at 6 natural log 5 minus. Ugh. Okay, so over here we have 1 over, you guys, this is 3 times 5 cubed. So that's 3 times 100.
Professor, we can't see your screen.
Oh, because I forgot to reshare it. Thank you. Ugh, such trouble here. This is great. All right, so you should see it now. So I was doing the 3 times 5 cubed on the bottom. So that's 3 times 125. It ends up being 375. So this is what I have in this bracket. Minus, you guys, we need to recognize something about the natural log of 1. Now you can put it in your calculator you want, or you can think about just the properties of logs. Any log of 1, so natural log, log base 10, log base 25, it doesn't matter what it is. If you take the log of 1, you get 0, and natural log is no different. So you guys, when I see the natural log of 1, I know that's just a 0. So I'm going to call it a 0. And if that's a 0, what happens to this entire term? Well, it disappears. So all I have over here is actually just minus 1/3. So keeping it exact until I absolutely have to put it in my calculator. Let's see what we have here. So I have 6 natural log 5 minus 1 over 375. You guys, this minus minus makes this a plus 1/3. And you guys, this is when I could put these two fractions together. If it did want an exact answer, you would need to do that. So you'd have your natural log term, and then you'd have this one fraction. If you put it in your calculator, you could probably just put all this in. But let's say you need to put your fractions together, because a lot of your homework, you're going to see places where you have to do that. So you need to just be up on common denominators, right? So you guys, I need to take this 1/3, and I need to make it a fraction that has 375 on the bottom. So how do I get from 3 to 375 on the bottom? Well, I had to multiply by 125. Remember, if you do it to the bottom, you have to do it to the top also. So this is my equivalent fraction. So what I have here is 6 times the natural log of 5 minus 1 over 375 plus, instead of writing 1/3, I'll write this as 125 over 375. And then you can put those two fractions together. So I have 6 natural log 5. That would be plus 124 over 375. So that this might be an example of an exact answer. If you needed it in a calculator, you just put it all in. You could probably just do it as long as you put your fraction in the parentheses. It should turn out just fine. So you guys, I'm going to do that. So just in case you're, working along and you want to check your calculator answers. So I'm going to do 6 times the natural log of 5. You guys, I get about 9.66 there. Then I'm going to leave that in there, like all the decimals. I'm going to say plus, and then in parentheses, 124 divided by 375. And you guys, what I get here is about 9.9, well, 9, if I round it to 2 places. So exact or calculated there. Luckily, we only have one more problem that I want to go through. And it's when you have a fraction exponent. So sometimes, in other words, this is a root, right? If it was written as a root, you would definitely write it as a fraction first, because remember, your goal is to do the power rule on it. So we have Well, when I'm taking the antiderivative, I don't need that anymore. You guys, so let's actually integrate. So if your power is 1/3, remember your n plus 1 here, you're going to take 1/3 and you need to add 1, but I'm not going to call it 1. I'm going to call it 3/3. So I can add those together and get 4/3. So 1 over n plus 1. So 1 over 4/3, x to the 4/3 is the integration. I'm going to take that from 1 to 4. Now remember, 1 over a fraction just flips the fraction. So 1 over 4/3 is really 3/4, x to the 4/3. Make sure you don't flip that one on accident. From 1 to 4. So let's put the 4 in there. So we get 3/4 times 4 to the 4/3 minus, let's put the 1 in there, 3/4 times 1 to the 4/3. So you guys, 4 to the 4/3 it's not an exact value. You could stick it in your calculator and approximate. Now, if you need an exact answer on this one, all you could really do, now let's talk about 1 raised to the 4/3 power for a minute. It's just 1, right? Because 1 raised to any power is 1. So really, this is just minus 3/4. And then as far as this goes, again, 4 to the 4/3 power is not an exact value. So if you had to leave it exact, you would just have to write it like this. This is as exact as it can get. But if you need to approximate, you can do, remember, you can do fraction powers in your calculator. You know, when you raise it up to whatever power, just make sure you put it in parentheses. So I'm going to do that here. I'm going to take 4 to the 4/3 power. You should, if you're following along here, you should get about 6.349 something here. So I did that. I'm going to multiply that by the 3/4 that's right next to it. So now I have about 4.7622. That's what this is. So about 4.7622. And then when you minus 3/4, or in other words, 0.75, you end up with about 4. Let's call it 0.01, if you had to approximate that. I wonder if the school lost power too. The kids' school. Sorry. Anyway, I just had a random thought come to my head. Okay, so you get about 4.01. So again, as far as answers go, just however they want it written. You are going to have some fractions today, so you might want to be reviewing common denominator stuff. You know, adding and subtracting fractions is going to be important. Other than that, you should be pretty prepared here for 13.4 homework, which I'll be putting up here. Well, yeah, I'll go ahead and get it up there, and it'll be due Sunday night. Trying to think of anything else I have to say. I can't believe our power went off again. I am so sad. Anyway, I will keep you updated. Hopefully it's just like a real temporary thing this time. But otherwise, I will just see you guys on Wednesday.